right, well, it's really nice to be here. I'm really honored to be invited and to be speaking in front of all of you, and excited to share Boeing's journey. So, this is a brief overview of what additive manufacturing is at Boeing, and we call Boeing Additive Manufacturing BAM, and we are all part of the family at Boeing, the people who work that. I had to say that because I saw the family earlier. So, we have 20 Boeing additive manufacturing sites worldwide, in the United States, Canada, Australia, and the UK. As was mentioned, we have over 70,000 parts flying in Boeing products, and these are airplanes, satellites, helicopters, autonomous systems, even starting new applications in submarines, so from the sea to space. These are metal and polymer. The majority of these are actually polymer, and I'll show on a timeline soon. And we have, since 2001, metal parts on products. Value stream capabilities, we have in-house a factory in the Puget Sound, Washington State, where we have the end-to-end value stream, and we also work with suppliers. And lastly, the digital integration is a really big aspect of BAM. So we focus a lot on modeling. Additive manufacturing is a digital process, right? And so we are connecting that digital thread. Currently, it's about 50% connected, including supplier processes where the data is streamed back in real time, where we can observe that. And that data is archived and formatted in a way that our engineers can easily access that in order to do their data analytics, the machine learning and data-driven models which are fed back into that value stream. We also then encrypt our build files, and we send those to qualified suppliers for a distributed manufacturing model where we can control quality and scale. So this is, I'm going to go very briefly. This is our polymer timeline. You can see it begins in 1990. Some of you were not born yet. Our first actual production parts were for the F-18. That's still ongoing. So we have polymer tubing and other parts inside of fighters. And we steadily increased, matured, became more complicated in our parts. And now we have 300 parts in the Starliner, the crewed capsule, T7, and our latest things, and on the International Space Station as well. For metal, we began about a decade later, and the first part was flying on the X-37A. You can see that's a near-net shaped part. And we have really methodically advance through time. In 2016, we have our first powder bed laser part. Actually, I take that back. That is a powder bed electron beam part in 2016. And then in 2017, we have this galley fitting and 7 other geometries that are in every Dreamliner since 2017. So there's, these are in production. And then the other parts, I've been rapidly trying to clear these through our comms group so I could share them. These are very new. The top 702, it was built on a M400-4, an EOS machine to get a size of the scale. And it's an assembly of 3 pieces, so it's about 1 meter, and it holds the engine of a satellite. So it's pretty critical. If that fails, the mission goes. The little command torn antenna, 2019, this launched on the Amos 10 satellite. Now that's only this big, but it powers up the electronics of the satellite. So if that fails, the mission's gone. And the O3B M-Power aperture cold plate, O3B is a satellite constellation. There's 11 satellites. They deliver internet to the other 3 billion people in the world who don't have internet access. That's why it's called O3B. And we have about 11 different parts in each vehicle. And the particular part there is multifunctional. It is a heat exchanger, it is a waveguide, and it's a structural component. So and there are many more that that I can't show you. Currently, we have about 3,000 different parts that are metal additive in flow. I mean, at this moment in time, in a certain part of the process for different satellites, for the MQ-25, which is the refueling autonomous vehicle, and then we have the parts on the 787. Okay, I'm going to go kind of quickly over some of our recent developments. This is a small sat. It's about this big cube, and it was invented in our Principal Senior Technical Fellows Garage during COVID. And now for Boeing, it's a product line. We are delivering the 24th such satellite. The first time in Boeing that we have a positive ROI, and we're really excited about that. Everything there is 3D printed, including the tank. And you can see with everything we do, we have coupons, witness coupons, fatigue and so forth, just really, making sure that our process is stable, repeatable, reliable. And you can see that we have a cost reduction of 30% over the legacy of the same, because there was a legacy satellite that this replaces. This is really exciting. This is the MQ-25 heat exchanger. The reason why I like this is because it's a fixed wing application, and one of the first powder bed fusion parts on a fixed wing. And this image on the left-hand side is the heat exchanger cut in half so that you could see the intricate fins. And there it is whole. And basically, if you were to make this traditionally, it would be brazed. And we found a lot of the brazed legacy parts, when we put them on the vibe table, they fail where these don't, right? Because where the skin and the fin attach, it's monolithic, there's no joints, and so it's much more robust. And the other application I'll just show you quickly is helicopter. So we have 15 of these Searchlight chassis that are in service with the customer. They've been flying since 2019. I'm excited about this application. This is a plate for an M400, so you can get an idea of the size. This is the most complicated testing program that we had, because it's a really high fatigue environment, right? A helicopter. So this is really exciting. So we redesigned it to this Millstand 810 environment for sand, for fog, for ice, for corrosion, for lightning strike. I put that picture in there because I just think it's cool. Anyway, so this is a really nice application that has been in service now for a few years, but I just recently was able to clear that. All right, so let's talk about sustainability. So I wanted to sort of set the stage where we are at Boeing. Now, overall, Boeing has committed to really reducing, the global impact of our products, and basically promised to decarbonize aviation through advancements in technology, additive, advancements in operations and infrastructure, additive, sustainable aviation fuels, separate, and carbon offsets. And so there's certain metrics that the company has said that we will reduce greenhouse gas emissions, water and solid waste consumption, energy use, and hazardous waste. And so with additive manufacturing, we have created a couple of case studies. There's one that is cleared that I can show you today, where we're looking at the same measures to align with Boeing's statement in greenhouse gas emissions, solid waste to landfill, water consumption, energy emissions, and hazardous waste. So, for additive manufacturing, we really look at the sustainability impacts in two different ways. One is how we make the part, and the other is the parts in operation, because additive manufacturing allows you to optimize the part so that your end product can be more streamlined, using less fuel to get you where you need to go, right? Because it has less drag because of what we can do with additive manufacturing. So at this point, I'm only going to talk about the manufacturing process because I don't have data yet, real data from the impact of the part produced. But you can imagine the gains that there will be. So this is really why additive manufacturing provides sustainability benefits. I think we probably know. Because of the intrinsic nature of additive manufacturing, there's basically less waste, right? I mean, so in theory, we use only the material that we need for the part, in theory. There's some scrap, but it's very small, and we'll get better at that. And then we can, optimize our design. We can optimize, apart from the fact that if we were going to make a heritage part, we'll use less material, but two, we can take that heritage part and we can optimize it further, right? We could use topology optimization, where we put the material really only where it needs to be to support the loads and remove it from everywhere else. And I think we're going to have a talk on that later. Eliminates primary tooling completely and all of the energy consumed with that. Reduction in transportation, and this is because we can print a part where we need it to be, but also because we have found that we eliminate a lot of parts. So people in my company say, Melissa, how many parts are you making? And I say, no, that's the wrong question. Ask me how many parts I'm eliminating, right? I have one, I think I can say this, I can't show you the picture, but we have one application right now where we have 41,000 parts. And these are a system of 1, 2, 3, 4, like 6 major parts connected by secondary parts, which are fasteners, right? And so we have 41,000 total parts, condensing that to 1,600. I'm eliminating 39,000 parts, and that's all of the energy, the transportation, the bookkeeping, really, the storage, the serialization of all those parts just goes away, right, with additive manufacturing. That's a real benefit. And inventory waste reduction, really, because we can create spare parts on demand, and because of the elimination of major and minor parts, and that's real. I think that's a huge benefit. So what did we do? We looked at the life cycle assessment, where we're taking cradle to grave, and we look at basically every aspect, the raw material extraction, from digging up the material from the earth, converting that material to a principal material in the case of additive, or a material that you can machine or forge for the case of traditional. We do the same life cycle assessment for both cases. And then we look at the manufacturing process in both cases. We look at the energy consumed, if there's protective gases, what kind of hazardous waste materials, how much water we use in each case, the transportation in terms of the energy consumed in transportation, and the transportation of the raw materials, of the procured parts, of the assembly, sending it to testing, sending it to heat treat, wherever you need to send it, the recycled materials back into the system, waste disposal to the end user, usage, and the end-of-life treatment, and reprocessing and recovering. So we look at this for both cases, and I can share with you our first case study. And this is for that part I showed you already. This was on our timeline that's in production on every 787 Dreamliner. It's been in production since 2017. Now, this part wasn't optimized for additive. It's just built additively. So it's not going to have any impact in terms of how the airplane flies, right? But it does have a huge impact on how it's made, right? And so we took this as our first case study. Now we're calling it cradle to gate instead of cradle to grave, because everything after the installation process is the same for both, traditionally manufactured and additively manufactured. And this is what we found. So the chart on the left-hand side, the blue, is the traditionally manufactured metric. The orange is the additively manufactured metrics. And so we're looking at the top 5 impact categories. And those are the 5 that Boeing was committed to reducing, right? And so we see the total energy consumed is 39% of the traditionally manufactured, global emissions 37%, solid waste to landfill 35%, total hazardous material use 32%, and water consumption 30%. And so to me, this is really impactful. And where does it come from? It really comes from the beginning part, the beginning part of the value stream, the mining the material, the converting the material, and the transporting that material. Because in the traditional case, you have a big hog out, you have a lot of material. And in the additive part, you use significantly less material. When we look at powder bed, or this is wire, but the energy consumption, it requires gas shielding, it requires stress relief, where the other doesn't. But still, those are much smaller, holistically speaking, than the energy consumed in the traditional case. So this was a really good example for us. We looked at other aspects. I don't want to call them secondary, because these are really important too. So we looked at other aspects of human toxicity, carcinogenic and non-carcinogenic, acidification of the soil, of the earth, water depletion, global warming, ozone, land use, a lot of very important metrics. And we found very similar, but around 30, I think that line must be, roughly, percent compared to the traditional case. So this is really nice data. And so this is, in the end, this is the case where we took the tie wire. We're working right now on a case where we're looking at powder bed fusion and manifolds, as opposed to tie wire and a bracket. And then the third we're doing is powder bed fusion and a sheet metal bracket. And I can already tell you that case is not going to be good. But it's not surprising, because a sheet metal bracket also has a horrible business case for additive in general. You don't want to do that, right? Because you could get there cheap. They're made easily. But we're basically trying to show where, which applications have a positive sustainability trade. And there's some that are very, very significant. And hopefully the next time I'm able to see some of you, I will have those cases as well. This is opportunity to get even better, and smart nesting to really take advantage of that recycling of powder. That's the little command horned antenna that I had on that timeline. This is such a nice design. I like to put it in there because there were 0 support structures used on that. It was redesigned from a legacy part that had about, I think there were a little over 20 parts. There was even a set screw for tuning the aperture, and there was actually tape. I mean, it was a clunky part. It was made all in one, monolithic, with 0 support structures. It was made for additive. That's smart, right? You don't need to have your sacrificial support structures for recycling. Everything we do is also guided by simulations, right? We no longer allow our engineers just to try it and it fails. Just try it again in a physical machine. That's so wasteful, right? Instead, we're simulating everything that we do. That's why these simulation algorithms are so important, right? And so we're looking at the benefits of multi-laser machines. They have more energy, but they're shorter, and so there's instances where that's better. Nesting post-processing applications. And wouldn't it be great if everything was just, powered by sustainable energy? Boeing has a couple of sites. I think Charleston is 100% renewable. Our factory's there. So I'm going to end it with a quote, and I like this quote a lot. Resonates with me. A society grows great when old men and women plant trees in whose shade they know they shall never sit. And I think this is really important. It's about doing something for the future, not just yourself. And so, everything that we do is really, really to help future generations. So with that, I have 33 seconds left. I can say thank you in many languages. All right.